In this section, we're going to look at several key ideas which have led to our modern understanding of atomic structure. The term atoms actually derives from the Greek word atomos, which means indivisible. The Greek philosopher Democritus, who lived around 400 BC, argued that if you took any substance and cut it, what resulted would be half the size, but still the same substance. He said that if you could cut something over and over, you would eventually reach a point where you couldn't divide it any longer and still have the same substance. It was atomos, indivisible. Unfortunately, the idea of the atom remained dormant until about the 1700s, when, building on the technological innovations of the Renaissance, scientists began to unlock clues about atomic structure. In the late 1700s, Antoine Lavoisier explored and cataloged a large number of chemical reactions. In the process, he observed that the mass of the systems which reacted remained the same. Based on this, he formulated the law of conservation of mass. This states that in chemical reactions, matter is neither created or destroyed. For example, hydrogen and oxygen react explosively to produce water. If you were to combine 4 grams of hydrogen with 32 grams of oxygen in a closed system and then detonate it, you would discover that the water that you produced had a mass of 36 grams. That is, you have the same amount of mass at the end of the reaction as you had at the beginning. With our modern understanding of atomic theory, we can understand that the atoms are rearranging. The hydrogen molecules and the oxygen molecules are rearranging to form water molecules, but the atoms themselves are not created or destroyed in the process. The law of conservation of mass is a really important principle. Let's look at how it might apply to another common reaction. In an acetylene torch, acetylene gas reacts with oxygen to produce carbon dioxide and water and a lot of heat. If 28 pounds of acetylene is burned, 88 pounds of carbon dioxide and 36 pounds of water are produced. How many pounds of oxygen gas would be used up in this reaction? Now, this seems like a complicated problem, but in fact it's very simple. We just need to recognize that we are reacting acetylene gas with oxygen to produce carbon dioxide and water. It says that we began with 28 pounds of acetylene and we produced 88 pounds of carbon dioxide and 36 pounds of water. Now, the law of conservation of mass says that whatever we had on the left side has to be the same as what we have on the right side. So this becomes just a very simple algebra problem. 28 pounds plus how many pounds is equal to 88 plus 36. 88 plus 36 is 124. So if we subtract 28, we find that x is equal to 96. In other words, there are 96 pounds of oxygen that react. Around the same time as Lavoisier, Joseph Louis Proust articulated the law of definite proportions. This law states that compounds always react in definite proportions and no others. For example, we mentioned a moment ago that hydrogen and oxygen combine explosively to produce water. By using an electric current, we can actually reverse this process. So we could write this as water in the presence of electricity could produce hydrogen and oxygen. Now, if we were to write this in a balanced manner, we would say that every 2 molecules of water react to produce 2 molecules of H2 and 1 molecule of O2. A simple hydrolysis apparatus is sketched at right. This apparatus consists of a central reservoir containing water that feeds into 2 side containers. If we fill both side containers with water and then connect it to an electric source, we will begin to see bubbles form as the water is broken into hydrogen and oxygen. We'll see oxygen collect on one side, we'll see hydrogen collect on the other side. However, what's interesting is as we do this, we'll see the gas form where the oxygen is collecting, and we'll see the gas form where the hydrogen is collecting. But we always form twice as much hydrogen as oxygen. We always see twice the volume formed on the hydrogen side as on the oxygen side. And it will always follow this. We'll always see a 2-to-1 ratio of hydrogen to oxygen being formed in this reaction. Here's another example that uses the law of definite proportions. When copper forms a compound with chlorine, it always forms one of the following two ratios. One, what we call copper 1 chloride, is 1 copper to 1 chlorine. The second one, what we call copper 2 chloride, involves the combination of 1 atom of copper with 2 atoms of chlorine. Now the first question is, if the mass of copper is 63.5 AMU, atomic mass units, and the mass of chlorine is 35.5 AMUs, what is the percentage by mass of chlorine in copper 1 chloride and in copper 2 chloride? In order to do this, we're going to start with copper 1 chloride, and we're simply going to take the mass of one chloride atom over the mass of the whole thing, a CuCl. Since the mass of one chloride is 35.5, and the mass of the whole thing is 63.5 plus 35.5. This is 35.5 divided by 99.0, which comes out to 0.358, or 35.8% chlorine in copper 1 chloride. Let's do the same thing with copper 2 chloride. In this case, we're going to have 2 chlorines over the mass of CuCl2. So this is going to be 2 times 35.5 over 63.5, the mass of the copper, plus 2 times 35.5, the mass of the 2 chlorines. That comes out to 71.0 over 134.5 atomic mass units, which is equal to 0.528, or 52.8%. So we see the law of definite proportions reflected here. Copper and chlorine react in one of two ways, either 35.8% chlorine or 52.8% chlorine. So what about this last question? Is it possible to have a pure compound of copper and chloride with a mass of 25 grams of copper and 20 grams of chlorine? Well, this would be a 50-50 mix, and so the answer is no. The only two percentages, the only two ratios that we're going to see are the ratios that we calculated above. We're either going to have 1 chlorine to 1 copper, or we're going to have 2 chlorines to 1 copper. These two ideas, the law of conservation of mass and the law of definite proportions, were very influential. In the mid-1800s, John Dalton, an English schoolteacher, articulated a framework for modern atomic theory. Dalton's theory contained 4 key points. First of all, elements are made of tiny particles called atoms. Secondly, the atoms of each unique element have a unique mass. Thirdly, atoms can join together in whole number ratios to form compounds. And fourth, atoms are unchanged in chemical reactions. Let's look at one more example that will tie together the law of conservation of mass with Dalton's view of the way atoms combine. Which of these does not follow the law of conservation of mass? I encourage you to pause the video for a second, take a look, and then we'll go through the solution together. Okay, so the key idea here is that with each reaction, we should have the same number and type of atom at the end of the reaction as at the beginning. In the first box, notice that we have 4 of the blue atoms at the beginning, and we have 1, 2, 3, 4 of the blue atoms at the end. Similarly, if we counted the yellow atoms, we would end up with 2, 4, 6, 8 of the yellows, and 2, 4, 6, 8 of the yellows on either side of the arrow. If we look at the second box, on the left-hand side we have 2 blue ones, on the right-hand side we have 2 blue ones. On the left-hand side, we have 2, 4, 6, 8, 10 yellow ones. And we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 yellow ones on the right. So in both of these cases, the law of conservation of mass is followed. However, in the third box, we have 4 blue ones on the left, and we have only 3 blue ones on the right. We have shown an atom being lost, and so this is not correct. According to the law of conservation of mass, you're always going to have the same number and type of atoms at the end as you do at the beginning. So are we able to see atoms? Well, historically, no. Atoms have been too small for us to be able to see, and so we always had to gather information about atoms indirectly. However, over the last couple of decades, a number of techniques have been developed that allow scientists to actually visualize atomic structure. One of the most dramatic examples came in around 1990, when scientists at IBM Labs were able to not only visualize atoms on a metal surface, but using a technique called scanning tunneling microscopy, we're actually able to manipulate atoms and spell out IBM. A more common technique for visualizing atoms is X-ray crystallography. Simply put, this technique measures the way X-rays reflect off of atoms in a crystal and creates an image of the atoms that are in the crystal. For example, the image shown here is a depiction of the atoms in hemoglobin. This is the protein that transports the oxygen in the bloodstream. X-ray crystallography allows us to see the way atoms pack together in a solid. So, in summary, there are 3 key ideas that you should take away with you. 1. Atoms are not created or destroyed. This is the law of conservation of mass. 2. Atoms can combine in whole number ratios to form compounds. And 3. Atoms are not changed during the course of chemical reactions. These 3 ideas are foundational to our understanding of chemistry.